In this episode, we take on a classifier that often surprises beginners because it can work very well even though its core assumption is obviously unrealistic. Naive Bayes is a family of probabilistic models that uses Bayes' rule to estimate which class is most likely, but it does so with a simplifying assumption that features are conditionally independent given the class. That assumption is rarely true in real datasets because features often influence each other, overlap in meaning, or come from the same underlying process. Even so, naive Bayes can be fast, stable, and competitive, especially for certain kinds of problems like text classification and high-dimensional data where many features carry small hints. The key is to understand what the independence assumption really means, why the model can perform well despite being naive, and where it tends to break down so you do not overclaim what it can do. By the end, you should be able to describe naive Bayes as a practical tool with predictable strengths and weaknesses, not as a magic trick or a model you avoid because it sounds too simple. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To understand naive Bayes, it helps to start with the central idea of Bayes' rule, which is a way of updating beliefs based on evidence. You begin with a prior belief about how common each class is, and then you update that belief based on how likely the observed features are under each class. The output is a posterior probability for each class, meaning the probability of the class given the observed features. The challenge is that computing the likelihood of observing a particular combination of features can be complicated because features can depend on each other in many ways. Naive Bayes makes this tractable by assuming that once you know the class, each feature provides independent evidence, so the overall likelihood is the product of individual feature likelihoods. This turns a hard joint probability into many simpler ones that are easy to estimate from data. The independence assumption is what makes training and prediction fast, and it is also what creates the model's characteristic behavior. The phrase conditionally independent given the class is important, and beginners often skip past it. It does not mean features are independent in general, because they may be correlated across the whole dataset. It means that within a single class, knowing one feature does not tell you anything about another feature beyond what the class already tells you. For example, if the class is spam versus not spam, naive Bayes assumes that the presence of one word does not affect the probability of another word appearing, once you already know whether the message is spam. In reality, words are highly dependent because language has structure, and spam messages often contain groups of related words. Yet naive Bayes can still work because it is not trying to model language. It is trying to separate classes using signals that are strong enough in aggregate. This is one of the most important mindset shifts. A model can be wrong about how the world is generated and still be useful for prediction if the approximation helps separate classes. A big reason naive Bayes performs well in practice is that it is a strong baseline that learns quickly and does not need a lot of data to produce reasonable parameter estimates. Each feature is modeled separately within each class, which means the model does not need to learn complex relationships that require lots of examples. In high-dimensional settings, like text where you may have thousands of possible words, more flexible models can struggle because the number of parameters grows quickly and overfitting becomes a real risk. Naive Bayes treats each word as a small piece of evidence, and when you have many small pieces, the combined evidence can be powerful even if the pieces are not truly independent. Another advantage is that the model's training is usually straightforward, often based on counting how often features appear in each class, and then converting counts into probabilities. That counting structure makes it robust to some kinds of noise and easy to update when new data arrives, at least conceptually. For beginners, it is helpful to see naive Bayes as a model that wins by being simple and additive in log space, rather than by capturing complicated interactions. It is also worth understanding that naive Bayes comes in different variants depending on what kind of data you have, and the choice matters for correct use. If features are binary, such as whether a word appears or not, a Bernoulli-style model can be appropriate. If features are counts, such as how many times a word appears, a multinomial-style model often fits better. If features are continuous numeric values, a Gaussian-style model assumes each feature follows a bell-shaped distribution within each class. The common thread is the same independence assumption, but the likelihood model for each feature changes. Even without implementation detail, the lesson is that you must match the feature type to the right likelihood model. Otherwise, the model will misinterpret the evidence. Beginners sometimes feed in continuous values to a count-based assumption or treat counts as continuous, and then are surprised by poor results. Thinking about what each feature represents and how it behaves within each class helps you choose the appropriate naive Bayes form. One of the most famous practical tricks associated with naive Bayes is smoothing, which is the idea of avoiding zero probabilities for unseen events. If you estimate probabilities from counts and a feature never appears in a class in your training data, the estimated probability becomes zero, and multiplying by zero would wipe out the entire likelihood for that class. That creates a brittle model where one unseen feature can dominate the decision, which is not what you want in noisy, real-world data. Smoothing adds a small amount of probability mass to every possible feature outcome, so that unseen does not mean impossible, it just means rare. Conceptually, this reflects the idea that your training data is incomplete and you should not treat absence as certainty. This is also a good example of how assumptions and priors shape model behavior, because smoothing is essentially a prior belief that every feature could occur. For beginners, it is enough to remember that naive Bayes is count-based and therefore sensitive to zeros, and smoothing is the safety valve that keeps it from collapsing when faced with new combinations. Now let's talk about where the independence assumption can hurt you, because this is where wise use becomes important. When features are strongly dependent in a way that affects class separation, naive Bayes can double count evidence, meaning it treats two correlated features as if they were two independent confirmations. Imagine two features that both measure almost the same thing, like two sensors that report similar signals, or two derived variables that are basically duplicates. If both are present, naive Bayes may become overly confident because it multiplies two strong likelihoods that are not truly separate sources of evidence. That overconfidence can lead to poor calibration, where predicted probabilities are more extreme than they should be. Even if classification accuracy remains decent, the probability estimates can be misleading, and that matters if probabilities drive decisions. Another failure mode happens when class separation depends on interactions, meaning a feature only matters when another feature is present, because naive Bayes does not model interactions explicitly. In those cases, it can miss important patterns or treat them as weaker than they are. A related pitfall is using naive Bayes without thinking about how features are constructed and whether they are meaningful. If features are poorly designed, highly redundant, or contain leakage, naive Bayes will happily absorb them because it is built to combine many pieces of evidence. Leakage is particularly dangerous because the model can become extremely confident by using a feature that indirectly encodes the label, and the multiplication structure amplifies that effect. Another issue is that naive Bayes is sensitive to feature representation choices, especially in text-like domains, where decisions about normalization, tokenization, or counting can shift what evidence is available. Even without discussing tools, you should recognize that naive Bayes depends on consistent counting of evidence across classes, and if the evidence is inconsistent or biased, the model's outputs will reflect that. Beginners sometimes interpret naive Bayes outputs as objective probabilities, but they are only as good as the evidence definition and the dataset. Wise use means treating outputs as conditional on the modeling assumptions and the training environment. Despite these pitfalls, naive Bayes often shines as a first-pass model because it gives you a quick read on whether the features contain signal at all. If naive Bayes performs reasonably, that suggests that individual features carry useful information and that a more complex model might improve further. If naive Bayes performs poorly, it could mean there is little signal, or it could mean the signal is primarily in interactions rather than in individual features. This diagnostic role is valuable for beginners because it guides your next steps without requiring heavy computation or complex architecture. Naive Bayes is also useful when you need a model that is easy to train and update, and when interpretability can be expressed as which features provide strong evidence for each class. While it is not as straightforward as reading a small set of coefficients, You can still inspect which features are strongly associated with each class under the model. That can help you spot data issues, such as features that are suspiciously predictive due to leakage or biased collection. Calibration deserves a special mention here because naive Bayes is notorious for producing probabilities that can be poorly calibrated, often too extreme. The independence assumption tends to make the product of likelihoods shrink quickly for unlikely combinations, pushing probabilities towards 0 or 1. That can make the model sound very sure even when the dataset is noisy, and that can confuse stakeholders who interpret probability as certainty. The wise approach is to separate the model's ranking ability from its probability quality, meaning it might order cases correctly even if the numeric probabilities are not trustworthy. If you are using naive Bayes for prioritization, extreme probabilities might be less harmful as long as the ordering is good. But if you need probabilities to reflect real-world frequencies, you must be cautious. This is another place where setting expectations matters. You can say the model is good at identifying likely positives, but you should avoid claiming the predicted probability is a precise risk estimate without checking. For the exam mindset, remember that probability output does not guarantee calibration, and naive Bayes is a classic example of that gap. To use naive Bayes wisely, you should treat it as a purposeful approximation that trades realism for speed and stability. You choose it when you have many features, when each feature provides small evidence, when you want a strong baseline quickly, or when data is limited relative to dimensionality. You become cautious when features are highly dependent, when duplicates or correlated measurements are common, or when the problem depends on interactions that naive Bayes cannot represent well. You also remain careful about how you present its results, especially probability claims, because the model can be overconfident even when it is accurate. For the CompTIA Data AI certification, the practical skill is to explain this trade-off clearly. Naive Bayes can perform well because it simplifies the likelihood calculation, and it can fail because the independence assumption distorts how evidence is combined. When you can articulate that, you are not just naming a model. You are showing that you understand why it works, when it works, and how to avoid common misuses.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.